Now that we've discussed the general why behind nonparametric statistics, as well as introduced the concept of bootstrapping, we can now talk about rank-based statistics, the KS test, and how nonparametric approaches can help when you have predictive problems. When we're talking about rank statistics, it's important to realize that we rank things in the real world all the time. When we talk about international rankings, which country is the happiest, which government is performing the best, we don't know what number a country is, right? We don't say necessarily that Sweden is 98 happy. We often say they are the number one happiest country and then rank countries 1, 2, 3. Same idea with sports. There's, the top performing team, the top performing player, the second top performing. Same thing with leagues or search engines or academic journals, prestige or reviews online, right? You have 1, 2, 3, 4 stars. These are all ranking, and using statistical approaches that use ranks as their input are what you would need to start analyzing this type of data. For example, sometimes you do have quantitative data and that gets transformed into ordinal data. So sometimes you start with rankings, 1, 2, 3, 4. Sometimes you have quantitative data, but it's not that it matters that 4.5 is 3.5 less than 1. It just matters their rank, which is often what we're doing in sports. Team that had the most points, we're just saying they were 1 and the other team was 2. You can transform quantitative information into ordinal data. And you do this by just using the relative rank between them. So 1 is the smallest number, 9.2 is the largest. And then we just rank each data point relative to one another. So if you have quantitative information and it ever says it's been transformed into ordinal data, what they mean is they took whatever the real numbers were and just ordered them by rank. And this is particularly helpful when we have data that have a ranking but no clear numerical interpretation, like movie reviews. So a reminder, ordinal data are a version of categorical information where the variables have a natural order, we talked about in the last video. One example of how to analyze ordinal data is with a very common and popular nonparametric statistical approach. And this is known as the Wilcoxon rank sum test. And you see that rank is right there in the name, or you can hear this referred to as the Mann-Whitney U test. I'm giving both names in case you Google to find out more about this. I want you to know that they're synonyms. What this test is helpful for doing is determining whether two independent samples were selected from the same populations having the same distribution. It is similar to a t-test where we look to see whether or not the means between groups were statistically significantly different than one another. But there is no requirement for a normal distribution in the underlying data set, and it tests the median rather than the mean, which is what t-tests test. Now, the assumptions still exist here, but you'll note that these assumptions make no assumption of the underlying distribution of the data. So the assumptions for the Wilcoxon rank sum test is that observations in each group are independent of one another. So you can't have group A affecting the observations in group B. And the responses here have to be ordinal, meaning if you have quantitative information, it needs to be put on a rank scale. And then the null and alternative distributions for this test. The first one for the null is that the distributions of your two groups of your populations are equal. And then the alternative would be that the distributions are not equal, meaning there is some difference in the medians between the two groups. An example question here would be, in a clinical trial, is there a difference in the number of episodes of shortness of breath between placebo and treatment? Right, you may want to know in group A and group B, your control and your test group, does the placebo versus the treatment have a different number of shortness of breath? So you might not be interested in how many episodes between them exactly, but whether or not there's a difference in the overall shortness of breath episodes between placebo and treatment. To answer this question, what you would have to do is have participants record the number of episodes of shortness of breath they have. These episodes from both groups would then be combined, sorted, and ranked, and we're going to do this in just a second. You would then resort the ranks into separate samples. Just going to fix my typo mid-video here. Great. You would resort the ranks into separate samples, placebo versus treatment, and then carry out your statistical test. So what this would look like is, here are your data that you start with. So it's a small study here to demonstrate this example. The number of episodes of shortness of breath are on the x-axis, and what we're looking at is a histogram. So you can see that there was one person who had 1 episode of shortness of breath and one person who had 12. There were 2 people who had 6 and 2 who had 4, right? So we have a small sample size just so we can see exactly how this test is carried out. What you then see are the number of episodes of shortness of breath for the people in the placebo group and the people in the new drug group. The next step after recording that was to calculate the ranks overall. So the first was the new drug. One person had 1. The next smallest was this person who had 2. So that person would get rank 2. There was one person who had a 3 shortness of breath episodes, so they would get 3. You would notice that there are 4 people who have 4. They would get rank 4 here for both of them. What you would see here now is there's one person who has a 5, 2 people who have 6, one person with 7, and one who has 12. So all you're doing is ordering from smallest to largest your sample data. Now, to convert from the number of episodes into ranks, you take that information and then just start from the lowest and go to highest. So this person would be 1, rank 2, rank 3. Since there are 2 4s, we split the difference and they're 4.5. So that takes both the 4th and the 5th rank. Then 6, split 7 and 8 to 7.5 because there's a tie, 9 and 10. So we've now ranked all of our observations. We have 5 people in the placebo group, 5 people in the new drug group from 1 to 10. So it no longer matters that this person had 12 episodes of shortness of breath. It just means that this person has 1 higher rank than the person before them. And then what we need to do is calculate the sum of ranks in each of the groups. So the placebo is 37 and the new drug is 18. Starts giving us a sense that there's a difference, but we need to carry out a test to see whether or not this difference is large enough using the Mann-Whitney U test. What this does, and the reason it's called the U statistic, is because we are looking at the number of elements in group A and the number of elements in group B and calculating our statistic for this sample of data. What TA stands for is the observed sum of ranks for sample A, which is what we calculated here. And NA is the number of elements in group A, and B is number in group B. If we look back at the data, what we would see is that the maximum possible value of TA is calculated in the green box. If we subtract the observed sum of ranks, we would then get our U statistic. When we do this for the data we're looking at, the U placebo is 3 and the U treatment is 22. When we think about how this number matters, 0 would be this minus this is exactly equivalent, and U would be 0. That's indicative of complete separation between the groups. Group A is completely distinct from Group B, whereas if there were no separation, N1 times N2 is the maximum possible value. The number of elements in Group A times the number of elements in Group B would be the largest value for U that you could possibly get. That would indicate there is no difference between the groups. And U is going to be somewhere between these numbers. As a reminder, our null hypothesis here would be low and high scores are approximately evenly distributed between the groups, right? There's no separation. The alternative would be low and high scores are not evenly distributed. This happens when U is less than or equal to 2. So between 0 and 2 indicates that there is a lot of separation, and you can start to think that these groups are distinct from one another. What we notice here, our U placebo in each of the groups is either 3 or 22, which is not less than or equal to 2. And we only reject the null if U is small, right? If U is less than or equal to 2. So in this case, what we would say is that while we saw there was some separating between the placebo and the treatment group, it was not distinct enough to reject the null hypothesis. So here, low and high scores are approximately evenly distributed between the two groups. So you wouldn't say that this treatment was just different enough from the placebo. So we fail to reject the null here. We've now talked about bootstrap, and we've talked about the Mann-Whitney U test, being able to look at the differences between groups using rank and median rather than the t-test, which requires a normal distribution and looks at means. Beyond this approach, Often you want to know, given limited samples from two populations, how do we quantify whether or not they come from the same distribution, right? You have two groups and you want to know whether or not they come from the same underlying distribution. So does sample B equal the sample from sample A? One way you can go about doing this is carrying out a KS test. So if you want to test whether a sample is drawn from a given distribution or whether two samples are drawn from the same distribution, you can do this empirically by comparing what we're saying here, cumulative distributions. So the cumulative probability distribution for two different distributions is plotted here, one with the red line, one with the blue line. And we, with the KS test, are finding the place across these two distributions where there's the maximum difference between these two cumulative distribution functions. For example, on the left-hand side, we have two distributions. Now we know ahead of time that the peachish one is from a normal distribution and the turquoise one is from a gamma distribution. Here on the right-hand side, the brown and the green are both drawn from two normal distributions. And at first glance, it's not clear whether or not these are drawn from the same underlying distribution or two separate. Now, I told you these both on the right are from normal, and these are from two different underlying distributions. But in the real world, you wouldn't know that. You would just have the data. So what you can do is carry out a KS test and plot the data looking at their cumulative distribution functions. And what we look at then is see that they do pretty much overlap at our eyesight. Now, we do see that the normal distributions overlap more. When we carry out a KS test here, which can be done in Python, we see that the gamma versus normal demonstrates that there is quite a small p-value, where normal versus normal has a much larger p-value, that there is no difference in the distributions being plotted here. Whereas over here, the difference between the two distributions demonstrates by the KS test that you do have two different distributions at the left. The last approach that I want to introduce when we're just starting to talk about non-parametric models is that when you have lots of data and no prior knowledge, you might want to consider non-parametric approaches to prediction. We talked about linear regression previously, and that has to do with when you understand the distribution of the data. When you have a whole bunch of data but don't really know the underlying distribution, you might want to consider non-parametric approaches to prediction. And the same thing goes for when you're not focused or worried about choosing the right features. If you don't require certain features to be included, or you don't need to know exactly how to interpret them mathematically or statistically, a non-parametric approach is a reasonable way to go. So if your goal is to fit training data while being able to generalize to unseen data, non-parametric approaches can be very useful. We're going to talk about a few, and we already have talked about SVMs a little bit and decision trees, or classification and regression trees. But we're going to focus in a little bit here on k-nearest neighbors, or KNN, and we're going to use examples of this throughout the videos. So when we talk about non-parametric approaches and we say that you don't require the distribution underlying the data to be drawn from any particular procedure, when we say that you can throw caution to the wind, right, and you don't need to meet as many assumptions, the question then is, why did I even spend that week teaching and using parametric statistics anyway? I want to remind you that parametric approaches are very helpful and exist, particularly because a lot of data follow these expected patterns. We have so many approaches to analyzing normally distributed data because a lot of data in the real world are normally distributed. Also, parametric approaches require less data and are more sensitive. When you take information from a quantitative scale and put it on a rank scale, you lose nuance and information in that process. So if you don't need to lose that sensitivity and those differences in the underlying data and can use a parametric approach, often that is the best approach. It's also quicker to run, train, and predict most parametric models, and they're more resistant to overfitting. Now, that's not to say that their parametric statistics are always the way to go. We've spent 2 videos now talking about when non-parametric approaches are helpful, and we're going to continue to talk about those throughout these videos.